Here's a problem. Let's say that your boss asked you to survey 2,000 people on their weight by tomorrow. After trying very hard, you only got 1,000 people to respond. You're still short of 1,000. What can you do? Well, you suspect that people's weights are normally distributed. So you figure that if you could find the mean and variance, you could generate as many as you want, and your boss would never tell the difference. So you're looking for the correct mean and variance. But how can you find them? Well, one way is to estimate them from the data you already have using maximum likelihood estimation, or MLE for short. But what is this likelihood function that you need to maximize? Well, let's look at this intuitively first and then make it formal. If you draw your data on a line, you could try to fit a bell curve to it. But if you put that bell curve all the way to the left of the data, it looks weird, because what are the odds that your data came from that bell curve? That seems very unlikely. So you decide to shift it to the right, where it looks a lot more probable that your data came from that normal distribution. In other words, what you just did was ask yourself, which bell curve gives me the highest probability of seeing my data? More specifically, you are asking, which mean and variance give me the maximum probability of seeing my data? Because you already knew it would be a bell curve, you just didn't know its parameters. Well, actually, we can't say that you're maximizing the probability because that would be true for a discrete random variable. But because we're in the continuous case, you are maximizing the probability density function instead. So now that we've developed the intuition, let's see how to formally define the likelihood function. Well, if we have a discrete random variable, then we define it to be the probability of seeing the data as a function of the parameters, where p is the probability mass function. If it is a continuous random variable, as in our case, we do the same but use the probability density function. Note that x is treated as a constant, and the likelihood is only a function of the parameters theta. That's why L doesn't have x in it at all. So, what does this look like in our case? In our case, we have that the likelihood is a function of the mean and the variance, because those are our model parameters. And x is our 1,000 values we already collected. So you can see that the likelihood function is really only a function of the parameters, because they are the only unknowns here. Now, if you collected those 1,000 samples independently so that they are IID, then you can write the likelihood function of all of these 1,000 samples as a product of the single samples PDF. Now, we hate working with products, so because applying the log to this function won't affect which parameters maximize it, then we apply the log and use the log likelihood instead, because this allows us to work with a sum and not a product. Now, here's a point of confusion. In books or papers, when you see the likelihood function, it will often already be the log likelihood. So you will often see it written like this, where the log has already been applied and we don't bother mentioning it. It's as though we define the likelihood function to be the log likelihood in the first place. Now that we have the log likelihood, we optimize for the maximum with respect to the parameters, which here are mu and sigma. In this example, we can find the maximum of the log likelihood function analytically by taking the derivatives with respect to mu and sigma and equating them to 0. But other approaches could be used, of course. If we continue this analytical approach, we will end up obtaining the maximum likelihood estimators, which are typically denoted with a hat. They are considered estimators because you use some data to estimate them. You can imagine that if you had collected a different set of 1,000 people, the resulting estimators would be slightly different. And if you look at the estimators, they also make sense with your intuition too. So, for example, when you moved that bell curve to the right to fit your data, you moved the mean to be approximately the average of your data points, which is exactly what we get here too. So what about that boss? Well, now you can generate the rest of the samples by sampling from the normal distribution with the maximum likelihood estimators, and your boss will never know the difference. And as promised, I'll leave you with what happened when I asked both Gemini and ChatGPT to generate that cartoon for me. And if you found this video useful, please consider subscribing.